Hey guys, it's Simon and welcome back to the LibGDX Kotlin RPG tutorial series. So in the last part we introduced the tiled map support, so we are now able to render some background layer, some foreground layer like the tree. We cannot move yet, so we cannot make our player hide behind the tree. We also create objects out of tiles, so for example the player and the slime entities so far. And yeah, that's it. So we also introduced an entity spawn system. So whatever we place in tile, so like we can see it here. So for example, the slimes, which are part of an object layer and have a specific type, like here. So all these entities or objects can be created in our game and we can use them. And now we want to add some more life into our world, let's say. So we want that our player can move around, that he can collide with certain things, that he cannot go through the fence or through the rock, for example, and all those things. And of course, we could do that ourselves. So if you never did something like this, so if you never did 2D collision handling, then I would suggest to do that first of all without using a physics system. So we are going to use a physics system. I just said it now. Yes, that's going to happen. But if you have never done that yourself, then I suggest to do it without a physics system first, because a physics system adds a lot of complexity, in my opinion, and also at the beginning it will not be that easy to understand. So in case you never did that collision, to calculate a collision between two rectangles, two circles, a circle and a rectangle and all those things, then I suggest to do that first yourself, to understand better what is then happening in the background. But we are going to introduce Box2D, which is a physics system that comes with libGDX. I think it's actually, you can use it for anything. I think it's written in C or C++. And yeah, libGDX added something to support that. And we use that for our world. So our player will be a physics so-called body, the slime will be a body, then there will be other collision objects for the tree, for the rock, so that you cannot move through that. And all this collision handling, movement and solving of collisions if it's going to happen, all of that is taken care of by Box2D for us. So how does it work? Let's close the spawn system because we don't need that anymore, and let's go to our game screen. So the core object of Box2D is a so-called world, which is a name clash with our entity world, and that's why I need to be a little bit careful with that, but it's not super complicated. So what we are going to do is create a physics world, and there is an extension function available which is called the create world, which is part of Box2D, where someone mentioned, I think in the first or second part of this series, that I forgot to add the Box2D dependency from libKTX. Let me quickly check that. So I have it here available, but I cannot remember. Maybe I missed that in the part, in the first part. So if you're missing this dependency here, so the KTX Box2D extensions, then please add it to your Gradle file and refresh it, because I might have missed it according to a comment. And this is what we need, because this create world is a KTX extension and it creates a so-called Box2D world. And what we can do with that, we can pass in a gravity. So normally Box2D works with the, I would say, international metric system. So it works with meters, it has kilogram as a weight. And what else? So that there are some metrics which are just standardized and which are used in there. And the gravity, for example, if you don't pass in anything, then it will be the normal Earth gravity, which is something 9 dot something meters per second, if I remember correctly. But in our case, we don't want that our entities are falling down to the screen. We want them to just stay where they are. So in our case, let's specify that explicitly. So our gravity is a vector 0, so without anything, no gravity on the x-axis and no gravity on the y-axis. And then we also want to do something in addition, which is a so-called auto clear forces, which I explain a little bit later. But basically we have to step our world. So similar like we update our entity world, we also have to update our physics world so that it moves the different bodies in this physics world around, that it does the collision handling, the movement, all of that is happening. And whenever you would call an update to that world, which we do that in a moment, then it would automatically clear all the forces. And what is a force? So to move an object in a physics system, you usually have to apply some force to move it. So an object like a human body has a certain weight, and to move a body along the ground, for example, you need to push it with a specific force to move it from A to B. And those forces will be cleared automatically whenever we call world.update, or I think it's called world.step in Box2D. And we don't want that, but I will explain that later on, maybe even in the next part. But for now, just write that down, that this clearing of the forces does not happen automatically. We want to do that manually ourselves. This is an important piece to have a correct physics behavior with the approach that we are going to use. Then for sure we are going to need this physics world at some point, so let's inject it to our entity world because we need it. Also, let's rename our world here to, for example, eWorld, to make the difference clear between the physics world and the entity world. And for now, that's it. So the only thing that we need to do is that we dispose the physics world when we no longer need it. So that's the initial setup. So with that, we have a so-called Box2D World, as you can see it here. And now we are going to add certain things to that world. So the second parameter, I did not explain that here. So this allows sleep. I think by default it is true. Yeah, exactly. It's true by default. What does that mean? So when we are going to add bodies to the physics world, then they will be considered when we update our world. So they will get checked. So if there is a force applied and they need to be moved, also if a collision is handling, how should it happen? So for example, if two balls bounce together, then they will move the opposite direction again when they collide, for example, and move away from each other. So all of that stuff is happening in the physics world. And when a body is sleeping, which per default is allowed, then it's simply not considered for the physics simulation, if I remember correctly. The reason for that is that that saves performance, of course, and computation power, because if it does not need to be considered, then no calculation is happening, and that is good. And that could be used, for example, I don't know, if you have, let's imagine a city simulation, and there are some people outside of the city and nothing is actually happening with them. So there is no, I don't know, no other people nearby, no car nearby. So they are simply standing around. Then instead of considering then in the physics simulation where you already know there is nothing happening with them, you can simply set them to sleep, and then they are not considered. And when they are important, you simply wake them up and do something with them. And yeah, per default, this allow sleep is true. So just keep that in mind, and so that you know what this sleeping is all about. Good, then the next thing is that we actually want that our entities in our entity world can have a physics body. So what a body is, I will also explain that in more detail in a moment. But for now, let's add a new component for that. So we will have a physics component, and this component has some information. So for example, it needs a physics body, which we cannot create initially like we did it with some other property of a component before. Was it the image? I cannot remember 100% anymore. But this body, so this physics body, will be created later on. It's not directly happening when the component gets created. And yeah, it's a so-called Box2D body, and this is the body in the physics world. So for example, you can imagine like a human being that is a body, and this body has certain so-called fixtures in Box2D, and a fixture could be the left arm, the right arm, that would be 2 fixtures. Then your main body itself, so the chest, for example, would be the third fixture, then maybe the head, the left leg and the right leg. So all of that are different fixtures, and the combination of all those fixtures is a so-called body. And then in the physics world, you can simply apply forces to that body, and the physics engine for us takes care of calculating how the different fixtures behave. So fixtures can also be joined together in certain ways, and you can really do very complex stuff with that, but we keep it very, very simple because we don't need a lot for our RPG. For us, a body will always be a box fixture, so it's, as the name suggests, a simple box, so like a rectangle on the screen, and that is it what we going to need. So we really have very simple box collisions, so rect collisions, and that's it for us. Good, then in our case, our entities already have an image, and we are already calculating the correct size, if you remember from the correct last part, so this relative size according to our world units. And we are going to introduce a helper utility so that we can create a physics body out of an image, so that the physics body has the correct dimensions at the correct size and is then aligned also with the graphic and the image that we are using in our game. So for that we are introducing a companion object, and there we add an extension function to our entity create configuration. So when we create an entity, we want to do something special, so we will add that to our entity spawn system in a moment, and we will create a physics component from an image. And what do we need to create a physics body? So there we need, first of all, the Box2D World. Then we need our image from Scene2D, which contains the correct size information and the position and everything. Then we need a so-called body type. So the body type in Box2D defines what kind of body you want to have, and there are 3 different types. So there's a static body that we are going to use for collision objects, so for example like a tree or the rock or the fence. So those are static objects that are not moving around, and for those you should give them the body type static body. Then there are dynamic bodies, so those are the bodies that we are going to use for the player and the slime, and those are usually bodies where you can apply certain forces, they can move around, and they will also interact then in the collision handling part, but in the difference to a static body, they simply can move, rotate, whatever, so they are not static. And then there's a third option which is called kinematic body, if I remember correctly. Let me check if I can find that. Yeah, so this kinematic body, and this is simply like a in-between body of a static and dynamic body. So I personally never used that, but from what I read, this is sometimes used in a platformer, for example, when you have moving platforms, which are not dynamic bodies because they have a predefined way, let's say, how they move and interact with your world, but they are also not static because it's not like a ground which always stays there. It's really, for example, a moving platform. So for such things you should use the kinematic body. But we don't use that. We only use a static body for the collision stuff in our world and the dynamic body for everything else, so for our player and for the slime, for example. Okay, and then we are also apply a so-called fixture action, which, as mentioned before, so a body without a fixture, I think actually does nothing in Box2D. So it always needs a fixture that it has some representation in the world, so that the physics world knows what are the boundaries and how does the body look like. And for us that can be different, so depending on what kind of entity we want to create, we will apply different or add different fixtures to the body. So that's why we make that configurable with that utility function. And what that is, so it's from a body definition, and there we pass in the physics component and two floats, which is the width and the height of the image. And then we can do something and create the fixtures according to our needs. So in a moment we will use this utility function. For now we just going to implement it and create the body, which is another core object of Box2D. So the world is the most important one, and then the body is the next one, which is very important. So what we need the position of our image. So where do we want to create our body? So there we have from our image. Do we have the position? No, is it X? Yeah, okay, so in C2D it's simply X, and we also have an image Y. And then we also have a width, which is from our image, the width, and we have a height, which is also from our image, the height. Then we return now something. So since we are part of the entity create configuration, so when we create an entity, let me quickly show you that to remind you, because that is something new. So in here, so world.entity, then in here you see that already you have this entity create configuration. So this add function, which we use to add components to an entity, this is a function of the entity create configuration. So we have that here. So we want to call now this add function, and we are going to add a physics component and specify something. So we do something with that. And what we are going to do is, first of all, we also need to return that. So we return a physics component, and then we can get rid of that because it's automatically infers the type and knows what we want to do. And now in this physics component, we need to initialize our body. So our body here gets created for the world, and there is a function, so world.body. Then we pass in what kind of body we want to create. By default, it's a static body, but we pass in our body type that we pass into the function. And then we want to correctly set its position and also add the fixtures to it. So the position in Box2D is a little bit special, because normally in LibGDX and so far what we did is that the position always refers to the bottom left of the image, for example. And in Box2D it's different. The position of the body is actually always the center, I would say, from all the different fixtures. So when we have a box, let me quickly draw here a box. Okay, so imagine this is our box, and until now everything was always the bottom left corner. But in Box2D it's never the bottom left corner, it's always the center, which is the position of the body. So this is something to keep in mind. So actually when we want to position now our body to correctly place it, we want to put it to the X coordinate, which is the bottom left of our image. And there we want to add the width of the image, but only half of the width. And the same for the height. So this is the position that our physics body needs to be aligned with the image that we are going to draw, because this is what we do in a moment. We want to have our physics body in the physics world, and the graphical representation, which in our case is the image, needs to be aligned with that. So there it's a little bit unfortunate that this is not correctly aligned, but it is what it is. So again, the physics body position will be the center of our image, and the image itself, so the position is the bottom left corner. So always keep that in mind, that when working with Box2D, you always add half the width and half the height to the position from your image or whatever other rectangle you use for a representation. Okay, then to optimize it a little bit, we also set certain things. So for example, the fixed rotation, we will set that to true. What that means is that the body could of course rotate, but we don't want that. So we simply want to have a box that does not rotate. We don't care about rotation. Our player cannot rotate around itself. So that's why we set the fixed rotation to true, which helps a little bit reducing the computations that are needed in the physics world. And then there is also this allow sleep setting, which we set to false, because in our world, to keep it simple, every entity that we create out of that should never sleep, so that the collision handling is always correctly processed. We could set that in the world as we've seen it before, so that we can simply say allow sleep to false, but maybe in the future on we would need to have it a little bit more granular, and for some entities we want to have allow sleep, and for some we don't. So that's why I set it here and not as a general rule in the world. Okay, then there is also the fixture itself that we need to add. So from our body definition, we apply the so-called fixture action. So this is the action that we pass in here at the top, and we pass in here 3 arguments, which is our component itself, so the physics component, and we pass in the width and the height, which we are going to use then in a moment. And that's it. So this is how easy it is to create a body in Box2D. So it has a position and then certain fixtures, and the fixtures is what we are going to cover next. So let's go back to our entity spawn system, where currently whatever entity we create, it has an image component and an animation component. And now we want to add something new. Now we want to add also a physics component to it. So there we introduced now this utility function, so we can create a physics component out of an image. And we want to need to pass in here is the physics world. Then the image that we have here from above. So let's store this image component here in a variable, so that we can then pass in the image component here below. Then we want to create a body type. So for now, to keep it simple, we just say it's a dynamic body. And then at the end, we have some certain fixture actions. So the physics world, we did not pass that in yet, but let's pass that now to our system here. So there we're going to have a physics world, which is a Box2D world. Good. And our fixture definition function takes in the physics component. It takes in a width and also a height. So that's it. Also, let's import that a little bit to keep it a little bit shorter, so that we have it on almost one screen at least, but that's good enough. So physics component, width and the height. And now we are going to add the fixtures to our body. So as mentioned in our game, it's very simple. So we just add a box to our body, and that's it. We will have in the future different fixtures to, for different use cases. We need different fixtures. You can imagine it. So for example, you have, maybe you heard of that already, you have a collision fixture, so which is the rectangle in the world, which is taking care of the collision that you cannot walk through walls, for example. But we will also have like how we call that, a sensor fixture, like for example an interaction circle around your body, and everything that is inside that circle you can interact with. So for example, to open a chest, we could have a specific fixture which is a little bit bigger than our collision, and everything that is within that fixture we can then interact with, just as an example. But for now, so in this part, we are just going to add a box. So what we need is a so-called box extension function, which is again coming from LibKTX. There we are going to pass in the width and the height from our method that we get in here, so which is actually the width and the height of the image. Then this box is a fixture, and there we can define it in a specific way. So there you see there's a so-called fixture definition. There are some important attributes that you should have heard of. So the first one is this sensor that I mentioned before. So a sensor is a fixture which is not interacting in the collision handling. So your body can have as many sensors as you want to have it, but the sensor will not block anything or, for example, push you away from a wall. So those are simply textures which still get notified when another body is colliding with them, or another fixture actually is colliding with them. So they get notified in those cases, but they don't do anything real in the collision handling. So as the name suggests, it's really just a sensor, nothing real. In our case, let's just set that, and we want to set that to false in that case. So we don't want to have a sensor. This should be a real box which is responsible for the collision handling. Then there is a so-called user data. So this is, did we use that already in Scene2D? No, but Scene2D has something similar like that as well. So a user data is simply any object, as you can see it here, which you can use for whatever reason. So for example, if we have then later on maybe a specific sensor which is only responsible to check if we interact with something, then we could give that a specific name, that this is, for example, our interaction sensor or whatever. And this user data you can then of course check in the collision handling that we learn in future parts and do something special with it. So this is more to identify what kind of fixture you are dealing with. And this is for personal use. Box2D doesn't really care what you enter there as a user data. This is really just for yourself. Then there is the friction, which I think has a value between 0 and 1. And there, for example, a friction of 1 would mean that when, again, you have a platformer and your player is, for example, jumping against a wall, with a friction of 1, he is then simply sticking to the wall and not moving downwards. But if he has, for example, a friction of 0, then he will not stick to the wall and simply fall down again. So this is the friction behavior. And there is another one, but I forgot how it was called. Let me quickly check. Okay, so it's the restitution, which you could also configure, but we don't need that in our world, and also the density. So if you're more interested in physics stuff, then those values might make sense to you, and you can then simulate certain behavior. For example, I don't know, a water has a different density than oil, for example, and you can play around with those values to get a more realistic physics behavior. But in our game, again, it's very simple. We don't need that, so we can simply skip it. And also the user data for that specific fixture, we are not going to set it. So the important part is here, so PhysicComp from image, we create a body inside that method. So in this case, a dynamic body out of our image, so with the correct position and size that we passed in here at the top. And then we add a box fixture to our body, which is not a sensor currently. So this is what we defined here. And with that, so now all of our entities would automatically get this physics component. There is one thing that we did not implement yet. Let's do that quickly, which is a physics component listener. And what we want to do here, so when a physics component gets added to an entity, sorry, we already have the component here, then from the body, we want to set the user data. So there's a user data on the body, but there's also a user data on the fixture. And on the body itself, we want to store the entity so that we later on know there is a so-called context listener in Box2D where we can then interact or do something when a collision is happening. And there we want to know what kind of entities are actually colliding, and to know which body is linked to what entity, we do that in here. So our component body, so from our physics component, we set the user data to the entity which gets that component. And when a physics component gets removed, then we need to clean up our body. So there, from our component, from the body which is linked to a specific world, there we want to destroy the body. So this is the cleaning up process of Box2D. And let's make it like this. So we have a body, which is the component body. And from that body, from the world, we destroy the body. And also the user data will be set to null. So let's do it like this. Maybe below, because I think destroy body is triggering if there would be a collision between two entities and you remove a body while they are already colliding, then this, from what I know, still triggers an event so that the collision gets resolved, so that bodies are not colliding anymore. And in that case, we might still need the entity information. So that's why we clear the user data after we destroy the body. Okay, and let's also register our component listener. So back to our game screen. Let's add another component listener, which is our Physic component listener. Good, then we have now entities with Physic bodies, but we never update the world. So if we would do anything with the entities, nothing would currently happen. So let's create a new system for that. So there we have a physics system, and this system acts on all entities which have a physics component. And later on we also need an image component, but we will not cover that in detail in that part. That will be in the next part. But for now, let's add that. And what the system needs is, of course, the physics world. Then it needs the image and physics components. And that's it for now. Then it is an iterating system. And then we are going to implement the onTick entity method. Okay, so now there is something important, and it's the first time now that we are going to use the first or second parameter of flex. It's actually the third one in this case, which is the interval, because what we want to have is a fixed interval. We don't want to update the system every time we update our entity world. We actually want to make that happen at a fixed time step. So our interval is a fixed interval, and we want to do that, for example, 60 times per second. And why do we want to do that? So there is a simple explanation for that, and the reason is that physics engines, they usually prefer that you make a physics simulation with a fixed timestamp, so that the delta between two steps is always the same, to be, first of all, more accurate with the calculation, and also to avoid certain problems. Because you can imagine you have a ball, for example. So there is a ball, and then there is the wall at the end. And when we now move this ball in that direction, so it moves towards the wall, then this is totally fine if the ball moves very small steps all the time. Then the physics engine will correctly detect the collision with the wall and bounce the ball then backwards. So that is totally fine. But what would happen if the delta time between two simulation steps becomes quite big? So imagine our ball is here, and in the next frame he would collide with the wall, but for whatever reason our computer was stuck, or our phone got stuck, or had some delay because of some computations in the background or whatever. And for example, there was now a delta time of 2 or 3 seconds, so a very long delay. So then the physics world would move this ball through the wall, because the the movement that it takes in that one step, so in this 3-second step, is, for example, I don't know, 300 meter, and then it will simply be after the wall. So it moved through the wall because the step was so big that it could not detect this collision properly. And to avoid such a problem, Physic engine, at least Box2D and most likely other Physic engines as well, but I don't have experience with those. At least Box2D prefers then here a fixed time step, and the documentation, I think they suggest either 60 frames or was it 200 frames, something like that. I usually stay here with 60. And with that one, you have always a correct physics behavior, and moving through a wall, for example, can never happen with that specific fix here. Okay, then I mentioned now also this big gap. So for example, if delta time would be 2, 3 or 4 seconds or whatever, and this is also a typical problem that could happen in games, and there is a very simple solution to that. So when we have our delta time here in our render method, then we can simply, let's actually do that here below because we only call that one time. So we limit that at most that it can be, for example, 0.25 seconds. So with that, we also avoid those super huge gaps. So I come to that in a moment, why that would be a problem again with physics engines as well, but also with normal games. You can imagine normally your delta time is very small because your game runs maybe very fluid with 60 frames per second or even more. But if you would have then specific stuttering for, I don't know, 2 or 3 seconds, and then your entire scene gets already moved forward 2 or 3 seconds, this is not a nice behavior that the player would like to have. So he doesn't want to miss a lot of things which is happening in your game simulation. And I think the word for that is called circle of death, if I remember correctly. You can Google for that. And to avoid that problem, you simply limit your delta time to a specific value. And this is actually also done by Scene2D internally. Let me show you that also. So in the render system itself, I think it's in Act, if I remember correctly. Okay, so in Act, if we would not pass in a delta time, you see it here, then it limits it so that the value that gets passed in does not exceed, for example, this 30 frames per second. So Scene2D has something built in for that as well. And yeah, we now have that as well because we simply take care in our game screen by limiting the delta time. Okay, then I want to introduce to you the so-called fixed time step approach. There will link an article in the video description below, and it has something to do with the problem that I described before. So again, imagine the ball and the wall, and we have now a fixed time step approach. So we run our physics simulation 60 frames per second. Which is good, but when it comes to rendering and all our other systems for the time being, they run actually every frame and as fast as possible, which would mean that our render system, for example, it could theoretically run with, let's say, 1000 frames per second, but our physics system actually updates all the images and the graphics only 60 times per second. Maybe you would reduce that to even less if your game requires that. For example, maybe just 20 times per second, and then the movement of your different bodies in that case, and also the images which are bound to those bodies, will not look that smooth anymore to the player. And to avoid that, we will introduce some interpolation, maybe not in this part, but then in the next part. So meaning that even though our physics engine maybe runs only 20 times per second, our rendering system can still run as fast as possible with, let's say, for example, 1000 frames per second, and then we do simply an interpolation. So imagine this is our scene before we update the physics world, and then after the physics world, maybe our ball would be, for example, here. So right before the wall. So those are the two steps of our physics world, and this is the first scene, and this is the second scene. And now in between, so the gap from this position to this position, in that gap our render system is running again and again because it's way faster. And to give now a smooth experience to our player, we will now interpolate the rendering. So we will smoothly move the ball from this position to this position in between two physics steps, so that the player sees a very smooth movement. So he will see the ball here, then here, then here, then here, until it reaches that specific position. And that is then called a time step with a fixed time step. So this is our interval with an interpolation. So that is the approach that we are going to use, and which is important to understand and to know. And again, I will link the article below that you can read more about it. But this is the implementation approach that we are going to choose, and with that you will see that we will have a very smooth rendering, and also the physics simulation is working just perfectly fine. Okay, so let me revert the interval to 60 frames per second, and now let's do some implementation. So first of all, as a safety, what I always do, so in the update method of a system, which is called every time we make an update to our world, in that case we want to check something. So if our physics world has the auto clear forces set, then this is a mistake. We don't want that. Then we want to clear it. So we reset it, but also we want to log here some information that we are aware of, that there maybe programmatically at some point we set this auto clear forces to true, and we don't want that because again, with our fixed time step approach, we step the world maybe multiple times per frame. I also come to that in a moment, and we just want to clear the forces once after all this stepping was done, to have a correct simulation behavior. So let's introduce here also a log. Okay, and in this case, let's just log an error, maybe in that case, that auto clear forces must be set to false to guarantee a correct physics simulation. Good, then we are going to call our update methods. Here I come to that in a moment, and when that is done, we want to now clear the forces, because since it is not done automatically for us, we need to do that manually, and we do that always after an update call. And what is an update call? So here Flex is taking care of that. So there are two types of intervals. So there's the default one, which is each frame, which means whenever we call world.update, then the onTick method of the system is called every frame. So this is the default one, and the one that most likely you need most of the time. Then there is a fixed time step approach, which is the one that we use for our physics system, where we only want to call the onTick method 60 times per second. We don't want to have that 70 times or 50 times or whatever. We want to have it exactly 60 times per second. And this is the implementation for this fixed time step approach, actually. So there is a so-called accumulator, which simply sums up all the delta times between the different frames. And at one point, this accumulator is greater than the interval that we define. So greater than, for example, 1 divided by 60. And when that is going to happen, then we call this onTick method and reduce the accumulator by this fixed step rate. So this, in our case, this 60 frames per second. And then that's it. So with that, we guarantee that our onTick method is called at a constant rate. And here you can already see, so why is this a while loop? Because theoretically, the delta time could be, again, very high. So in our case, the highest one would be 0.25 seconds. And 0.25 seconds, I don't know it now by my head, but maybe we could run there 2 or 3 times our simulation with our fixed rate of 60 times per second. So in such a case, with this fixed implementation, if the delta time was big enough, we might need to do not just one step in the physics simulation, we might to do 2 or 3 steps to catch up again with our simulation. So that's why there we have this while loop around that, which means then also that the onTick function of a system could be called multiple times with just one call to the world update of our entity world. Just to keep that in mind. But the important piece is simply to remember that with this fixed interval, the onTick method gets called at a fixed rate and not every frame. So this is the important part that you need to know about that. Okay, and what do we want to do? So in our onTick method, so this 60 times per frame, we want to call, of course, the normal onTick method, so that we also go through all of our entities. And we also want to step now our physics world. So there we make a so-called step call. Then we use here our delta time, which is this 60 times per second. And then there is a so-called velocity iterations and position iterations argument, which is just how many computations should be done in the physics simulation for velocity computations and also for position computations for your different bodies. And there, according to the documentation, a good value is, for example, 6 and 2. So we just take the values from the documentation of Box2D and stick to those values. So with that, now we update our physics world 60 times per second. And whenever that is done, so after the stepping is done, then we clear the forces. And here you need to remember now that this step could be called multiple times, so 2 or 3 times if the delta time is big enough. And between those steps, we don't want to clear the forces because we are not done with our simulation yet. We are only done after the update call here. So this is the reason why we have this auto clear forces set to false and why we clear the forces manually, because coming back again to the update method in here with this while loop, theoretically you could have multiple onTick calls and you don't want to clear the forces immediately after a step call. You really want to do that after one fixed update iteration. Okay, and as a final part of this part here, we are now going to update our physics body, or actually our image position, with the position of our Box2D body, so that our visual representation, so the graphic of the player and the slime, represent the physics position of our entities in the physics world. So to link that together with Box2D. And what we do here, so for the time being in this part, we are not going to introduce the interpolation. We do that in the next part. Here we really just simply set the image position to the position of our physics body, and that's it, without any interpolation, which is not a problem because at the moment nothing can move in our world. So we don't need the interpolation for now and can keep it simple for this part. So we need our physics component from our entity, and we also need the image component of our entity. And then we simply say from our image component, the image, there we set the position of that image, and what is the X and Y coordinates. There we can simply define it here. So we have the body X and the body Y position, and that is from our physics component, from our body, it is the position. And there we can import a LibKTX extension to have the destructuring available from Kotlin. And now we simply pass in here body X and body Y. And there, keep in mind, that would not be correct because the body position is always the center of the box. And we want to have the bottom left actually of the image, so the set position is setting the position of the bottom left corner of the image. So what we need to do is that we need to reduce here by the width and by the height. So for now, this is simply from our image. Let's put it inside, for example, a run block. And there we reduce the width from our image and the height, and only half of it, to have then the correct position. Okay, so we did not add the physics system yet to our entity world, so let's do that, and we want to do that before we render everything. Because here we spawn, for example, the player and the slime. In the physics system, we then updates the position of the image to the correct position of the body in the physics world, and afterwards we do then the rendering. So which means now when we would start our game, we should see actually exactly the same as we did before, but in the background we already have physics bodies. And I'm surprised we actually see that. And how would anyone now know, hey, is there really some physics engine stuff going on in the background? Are you lying to us, Simon? We don't believe you. And of course, I expect that you would say something like that. And let me prove that to you and quickly introduce another, would say, very nice concept that you should do when you develop a game. And for that, we are going to introduce a very small and quick system, which I normally call a debug system, which helps with debugging certain stuff. And this debug system, what it needs for now, we need again our physics world, because we want to debug our physics world, that we see where are our bodies, how are they moving, and all of that stuff. And this is simply an interval system for the time being. So it does not iterate over any entities, and enabled here is true, but we could disable it if we don't want to debug anymore. But for now, of course, we stick to true and implement the onTick method. And what do we want to do? So in Box2D, there is a renderer automatically available, which helps with the debugging of the world. So there we define a so-called physics renderer, which is of type Box2D debug renderer. So this is this debug renderer in Box2D that can be used to draw your physics world, but just in lines. So there you see that in a moment, it's really just some shapes and some lines. And in our init method, if the system is enabled, then we want to create this physics renderer. So there we create the Box2D debug renderer. And in our onTick method, there we simply now call the render method. And we pass in the world that we want to render. And we also need to pass in the camera matrix again with all the other render methods that we have. So what we also need here at the top is the stage from scene 2D. And then we can use from the stage the camera. And then, of course, we need to dispose something, because if our system was enabled, then we want to dispose our physics renderer. Okay, now let's add this debug system to our game screen. After our render system, for example. And now let's start the game again. And now you see those very big rectangles around our entities, and those are actually the Box2D bodies. So it is really working. So here again, the important part was, so the debug system, what is it doing? So first of all, it makes a difference if you add the debug system here or here, because let me quickly show you that. When we would move our debug system in front of our render system, what do you think is going to happen? You don't see anything. And why is that? The reason is that our physics renderer here, so the Box2D renderer, is just drawing those shapes, so the rectangles that you saw there. And if we would call that before our render system, then of course those shapes still get rendered. But if our render system afterwards is then drawing stuff on top, so like our tiled world and the entities and so on, then you don't see those shapes anymore. So that's why it's important to move the debug system after the render system, so that all the rendering that is happening in here is happening then on top of our normal game world, so that we see the shapes. And one other thing that you might notice here, so you might ask yourself, hey, why is there such a huge gap between the graphic itself and the Box2D body? Did we do something wrong? And no, we did not do something wrong. Everything is correct. And the reason for that is, again, the original graphics that we have from this asset package. So let me quickly open up, for example, the player graphic. And there you will see that there's actually a lot of transparent space around the graphic, which is not really used. And that's the reason why you see that also then, of course, in the game. So let me zoom in here. So as you see, the player graphic is just this small portion here. And around that player, there's a lot of space which is not needed. And this empty space is then actually what you see here. So this is exactly also that empty space around that player. So that's the reason. Again, you could of course optimize the graphics to reduce that, but I did not bother with that. And also, let me tell you, you will always have these issues when you rely on free graphics that you get from itch.io or opengamearts.org. And we will implement a solution that we can simply help with that, and we don't need to touch the graphics at all. We will simply reduce the physics body in the width and height. We will also offset it a little bit, and we do that then programmatically in our spawn configuration in one of the next parts, so that you then really, or that we can then really easily define and also adjust the physics body to the correct graphical representation in the game. Because also the player, of course, the player itself only sees that graphic here, and he would assume that that part here is colliding with the world. He will not expect that the original graphic is actually that big and that we will already collide with the tree when we are meters away from that. So that is, of course, does not make sense. So we will fix that in a different way. Okay, but that was already it for that part. So that was the first introduction to Box2D. Again, if you never worked with a physics system and you never did anything with 2D collisions so far, then I would not suggest to start with a physics engine. As you see, it's a rather complex topic. We are doing a very simple implementation here and very easy stuff, but still it's already quite some complex things that are going on in the background. And for a simple game like that, you can easily get away with implementing it yourself. And to summarize it once more, so to recap on what we learned now in this part. So again, in our game screen, we created the physics world. We set it to a gravity of 0 so that our bodies are not moving around automatically. We really only want to move them when we press a certain button to move them around. Then we set this auto clear forces to false, because we don't want that from our world, when we call the step method, that the forces get automatically cleared. Because if we would do that, then the physics behavior, especially with movement and jumping, would not be correct. And for example, if you want to have a game like in Super Mario, where Mario can always jump, for example, 3 tiles or 2 tiles high, and this should always be the exact height, no matter how you jump or how many times you press the jump button or things like that. If you want to have a correct behavior like that, then you need to clear the forces yourself, which we are going to do, and that's why we set that to false, that we always have the same physics simulation behavior. Okay, then we introduced a physics component, where for now we simply create this so-called physics body, where we create a dynamic body, and in our spawn system we add now these physics components to our entities. We make a dynamic body, we make it out of an image so that we already have the correct position and size for that, and we create only, or we add only one fixture to our body, which for now is this box and which is not a sensor. And then we have our physics system that we are going to enhance now in the next part as well, where we already introduced a fixed interval, which is 60 times per second, to have a correct physics behavior and simulation. And in this system we are aligning our image, so the graphical representation of our entity, with the real position of the physics body in the physics world. So this is how we combine that. And finally, to debug certain things, for now we debug the Box2D world, we introduce quickly a debug system where we simply render our physics world to see that the bodies are really available and the size and all the things that we are setting is done properly. Okay, with that, that's it, and thanks for watching, and see you in the next part. Bye bye.